Hello, everybody. Thanks for joining us today. You are part of the 250 people worldwide who have registered to this webcast entitled "The Sleeping Substrate Giants Are Awakening." This webcast is presented by Yole Development with the participation of System Plus Consulting and AT&S. My name is David Jordan and I am Global Sales Support Coordinator at Yole Development. Before we start, let me give you some practical information. You will have the opportunity during the whole webcast to submit questions. To do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions as time allows us, and for the remaining questions, we will follow up via email with all the participants. Concerning the materials and the webcast contents, please note that the presentation will be available and downloadable in the resources section of the platform. You will receive an email after the webcast with a link to the recorded session. So today, Yole Development, System Plus Consulting, and AT&S will share their analysis with you on the advanced substrates market. First, let's start with an introduction on the recent market forecast by Mario Ibrahim. Mario is technology and market analyst at Yole Development and specializes in the advanced packaging. It's your turn, Mario.
Thank you, David. Hello, everyone. Hope you're doing well. I'm Mario speaking. I'll be your first speaker for today. I will start this webcast with, let's say, a more generic market and trends presentation on three different advanced substrates. So the outline for this presentation is going to be separated to three main sections. I will start by a quick segmentation to explain you a bit the other chapters of this presentation. You hear me? It seems that we have a small problem. Trying to figure something out in here. Is it better now, David? Is it better?
Good.
Okay, so sorry everyone. I'm gonna start again. So today's outline is the presentation. This one will be more on the market debrief of all the advanced substrate markets. So my presentation is gonna be divided into three different sections. I will start by a market segmentation to explain each and every section in its detail. So the first one will be advanced IC substrate, followed by substrate-like PCB, what we call SLP, and embedded die, before concluding. So let's jump directly to the market segmentation. And let's start by this advanced IC substrate platform. What we call at Yole as advanced IC substrate is any layer that will serve as an interconnection between the top IC chips and the bottom board. The bottom board is what we call mainly PCB, what is called mainly PCB in the market. This kind of platform is having some line spaces less than 30 by 30 micron and above 5 by 5 using processes like MSAP and SAP. The second one we will be talking about is SLP, substrate-like PCB. which is an advanced board technology, meaning that it's a sort of evolution of the HDI boards, but the difference is that it's using MSAP and SAP once again, and it can go down to line spaces like 10 by 10 micron. And the last one is embedded die, which is a bit different because this platform is more a package itself and more a stack technology, meaning that the players embed some dies into the substrate, and then they can put on top different other dies. And this one is also using MSAP, but it can also use subtractive process for some different kind of discrete devices. If we look at the common point between those three platforms, we'll find that we have at least three common points between those platforms, which are reduced footprint, increased die integration, and increased performances. I don't know if that sounds familiar to some of you, but those three trends, in fact, and common points are exactly the same as the advanced packaging platforms. And this is why I entitled this webcast, "The Sleeping Substrate, the Giants Are Awakening," because we finally see a huge amount of innovation coming to the substrate manufacturers in order to follow the market trends, which are mainly those three parameters. So now I will go more into the detail of each and every of those platforms. So the advanced IC substrate, if we position this platform within the substrate landscape, we can put it between the board platform and all the back-end wafer level and panel level advanced packaging platforms, meaning that the advanced IC substrate is somewhere between substrates that are compatible with 5 by 5 to 30 by 30 micron line space. In this kind of platform, as I said, it's advanced IC substrate. It's let's say it's it's more like the intermediate layer that serves as interconnection between a chip and a board. To be more clear, we focus on two different types of substrate, which are the flip chip BGA and the flip chip CSP, into this section. What's new in this advanced IC substrate? In fact, in 2018, and especially at the end of 2018, we heard that there was a shortage in the supply of advanced IC substrate, especially the flip chip BGA. And when we dig a little bit more on this information, we found that the new platforms like the 5G base station and the old 5G infrastructure added to the high performance computing markets were sucking down all the flip chip BGA volumes. So in fact, we saw a bit an increase in the ASP of the flip chip BGA at the end of 2018. On the other hand, let's not forget that there's the flip chip CSP. And in this kind of platforms, the flip chip CSP is like more than 75% of the total revenues of the advanced IC substrate. So we should not forget that it's the biggest part versus the flip chip BGA. But the trend of flip chip CSP is that the growth is slowing down a bit because the main market driving the CSP is the smartphones. We all know that in 2019 the growth of the smartphone is getting low. And in fact, the demand is a bit sluggish for smartphones. That's why the flip chip BGA, as for today and in the future, will get more and more interesting as a platform, and it will gain a bit market shares from flip chip CSP. There's also a major trend in this field today is that many players are switching from subtractive process into MSAP, and this switch is driven also by all the footprint and the integration trends, meaning that everyone is willing to reduce the footprint of the substrate, and to do that, there's a way is to decrease the line space and have more and more IOs on the substrate using MSAP. And we are starting to see that even China, which normally they are labeled as a low-end substrate manufacturers and that are very, very well placed in let's say conventional board and PCB market, they are starting to enter this kind of advanced substrate competition. What is what is driving the flip chip generally? If we plot three different markets, which are wireless and sensors, mobile and computing and HPC, versus the package size and the number of IOs, we will see that the wireless and sensors are relatively small packages with low IO, while the computing and HPC are relatively big footprint packages, and that require a huge amount of IOs. And there's an in between those two different markets, which can be resumed by summarized by APUs in mobile, which are, let's say, at the same distance between wireless and computing. It means medium size plus medium IOs, number of IOs. On the other hand, if we put the type of substrate in front, you will see that that the flip chip CSP is mainly used in those wireless and sensors where they require low number of IOs and where the chip size is quite small. Once we go into more, let's say, complex devices in mobile and computing and HPC, you will see that the flip chip CSP is gonna disappear almost. There's always flip chip CSP used in here, but let's say the proportion is getting more into the flip chip BGA for mid and high IOs and mid and high package sizes. For the computing and HPC, in fact, it's one of the markets driving this growth of flip chip BGA, because in here, in terms of computing and in terms of performances, we need many IOs, and we need to mix different types of let's say packages. We will see some advanced packages like the 2.5D and the 3D mixed with the flip chip BGA. So to summarize, flip chip CSP is covering applications with low IO and small die packages, while the flip chip BGA is on the other hand covers application with high IO and larger package sizes. And to conclude on this first platform, just to give you a quick idea about the market, this market is gonna roughly double in the coming 5 years, passing into $8.3 billion with an 11% CAGR, mainly driven by the flip chip BGA. And with that, I will stop talking about the advanced IC substrate and I will jump to the SLP. So this is our second platform. The term SLP is confusing. Not all the industrial substrate manufacturers are used to use SLP, which is substrate-like PCB. So in fact, to ease the comprehension, let's say that SLP is an evolution of HDI by replacing subtractive process by MSAP process, meaning that the line space can be reduced using the MSAP process. And we place the SLP in between 10 by 10 and 30 by 30 micron line spaces. We may see some SLP going a bit lower than 10 by 10 in the future. Same, we were talking about SLP, but let me be honest with you. We asked ourselves several times before having an SLP chapter in our report, because in fact, it was unclear where this technology was going when we started to look into it. And when I say it was unclear, it's because till 2017, it was a one customer based technology. In fact, many players started to develop SLP. AT&S is one of the first players developing this technology for mobile phones, and the customer wasn't Apple. But after 2017, we heard some rumors that it seems not quite precise, that SLP may be stopped. And in fact, this is where we started to dig a little bit more. And in 2018, we saw that Samsung jumped into the use of SLP in their mobile phones. And this was, let's say, the new starting point for the SLP, because we started to see substrate manufacturers investing and implementing SLP lines like Mako and ZDTech and others to answer this demand. But in fact, let's say that the game changer for SLP will be this year. Why? Because in fact, we'll have a third entry, which is Huawei. And the most important thing is that Huawei is also entering not only the smartphone, but they will also enter and use the SLP for different kinds of applications like tablets and maybe for their smartwatches. So this is where the game is changing for SLP, because it's passing from, let's say, 1 or 2 customers to at least 3. And not only for mobile phones, meaning that the market is going to be broader and more possibilities for SLP are coming. Just to give you an idea, Huawei, they use the SLP in their latest Mate 30 smartphone that I think it was out this year. Why this SLP is quite interesting, let's say, as it was mainly driven and still driven by mobile phones, one problem of the mobile phones is the battery life. So if we compare the iPhone 6 to the iPhone 8 and iPhone X, we will see that the first level of improvement is passing from subtractive to MSAP. So MSAP is the process for SLP. They managed to reduce only 2% of the board area. The big jump was between the iPhone 8 and iPhone X, because they've done 2 different things. They didn't touch the MSAP process, so they kept the same line spaces, but they stacked two different SLP substrates, the one on top of the other. By doing that, they were able to reduce the board area by 15%, and this reduction allowed them to separate their battery and to put 2 different batteries into the smartphone. That means that they have a better battery life management in the iPhone X. It's somewhere related to the fact that they managed to reduce the board area. So this is a very important, let's say, driver for the SLP usage. Who is doing what, in fact, in terms globally, but let's focus on SLP. So as I said, SLP is today MSAP process. Maybe in the future it's gonna get to SAP. Today there's 3 main countries in this that are in a fierce competition: Taiwan, Japan, and Korea. Taiwan, they are the masters of high volume manufacturing. Japan, they are the innovation center, and South Korea, let's say, they follow the innovation, and they may position themselves as a high-end MSAP and SAP players. So in fact, the competition between those 3 countries is fierce. But let's not forget China. China was labeled till almost now as a low-end substrate manufacturer. But in fact, China is benefiting from the other players and the other countries transferring their lines, their advanced substrate lines into China. That means that we see different players, for example, transferring their SLP lines into China. So the Chinese are starting to get more and more used to this type of processes, which are MSAP. And we heard that many of those players have also an eye on the SAP process that they will start to implement very soon in the coming 2-3 years in their plants in China. Concerning Vietnam, Vietnam is considered as an emerging country, which is also benefiting from this SLP production line transfer to it. As for example, Mako done, they transferred the SLP line into Vietnam. And let's say they have a very good knowledgeable workforce, but they still are labeled as low-end substrate manufacturing. But this country is getting more and more interesting on the substrate manufacturing landscape. And Thailand, we can call them as a possible speculated good country for the future in terms of substrate manufacturing. Now, to conclude on this SLP section, you will see that the market is getting bigger and bigger. In 2018, the market, the $987 million, was only a smartphone market. In 2024, the $2.5 billion market will be split between smartphone, tablets, and smartwatch. Smartphone will still have the biggest, let's say, revenue in terms of advanced IC substrate, but tablets and smartwatches are entering this, let's say, $2.5 billion market. The last platform, which is embedded die. Embedded die is, let's say, a relatively new technology that is not that popular as the previous two platforms. We consider it as a platform that can go down to 10 by 10 micron line space and can go to more than 100 by 100 line spaces, meaning that it can use subtractive and or MSAP, depending on the application and device. When I say embedded die, it can be one die, passive or active, or even multiple dies. So what is happening in this market? Let's start by the breakthrough. In fact, today the embedded single die, the substrate manufacturers, they master the process and they reach almost 98% of yield. So this is not a big deal for them anymore. But in fact, the trend is to embed more and more dies. And when I say more and more dies, it's today the information we have is still at least 30 passives and 1 or 2 actives. So this is the next challenge for them, is to improve the yield when embedding multiple dies. What we see on the other hand in terms of investments, we saw huge investments. I can give you the example of Axis Semiconductor, which is a Chinese company, and Schweizer, which is a European company. They are both investing huge money in new Chinese plant. And what is interesting in that case is that almost 70% of their plant capacity will be to produce the embedded die. And the market will need this kind of high volumes because we are starting to see new applications like CMOS image sensor. We are seeing more and more mobile phone players implementing embedded die like Huawei, and it can be a very good technology for the 5G market. Let's not forget that this embedded die technology is mainly, let's say, for power devices. Why power? Because it has a very good heat management. By embedding the die into the substrate, you can do a double-sided cooling. So in terms of heat management, it's a very good solution. At the same time, it's also a good solution for signal transmission and better electrical performances. So in fact, mobile was the main market for this technology, but today, let's say, the markets driving this technology are no more the mobile, but are the automotive and the telecom and infrastructure. To give you just an idea, I just said that automotive is a market driver for this technology. This is an example of the commercialized product, which is a product from GaN system using AT&S embedded chip package die. And the application of this GaN transistor, in fact, AT&S is embedding GaN transistor into the substrate, and the final application is 48 volts vehicles. In terms of R&D, Schweizer are working on different other applications like the headlamps and some radar, where they are embedding the high frequency device, and for the LEDs, they are embedding some passives and the LED driver. The market was very small in 2018, but it will get bigger in 2024. It will reach 230 million, driven by automotive and telecom infrastructure. That slide, I will stop my presentation, but before finishing, let's conclude with some bullet points. In terms of advanced IC substrate, the mobile segment is let's say, is having a saturated growth. So the value creation is coming from somewhere else, which is the 5G and HPC. Flip chip CSP is still dominating, but BGA is gaining market shares. The competition is fierce because it's an $8 billion market. In terms of SLP, Huawei is a game changer. It's a $2.5 billion market. And for embedded die, it's still a new infant technology. It will require some standardization, but the market is big and is gonna be big in 2024, $130 million. So maybe it will be a push for new players to step into it because it's still a few players involved in it. And with those words, I would like to thank you for hearing me, and don't hesitate if you have any questions at the end. Thank you.
Sorry, we have some technical problems. So thank you very much, Mario, for your great presentation. We will now continue with the technology review. This presentation will be held by Stéphane Elisabeth. He is a custom analyst expert in RF, sensor, and advanced packaging and system plus consulting. Stéphane, it's your turn.
Thank you, David, for the introduction. Hi, everyone. I'm Stéphane Elisabeth, a cost engineer at System Plus Consulting. I'm in charge of RF, sensor, and advanced packaging, and I will present you some technologies using advanced substrate, especially in the consumer world. So to begin with, I will present the company. So here at System Plus, we provide reports on several devices in main application domains. In the case of advanced substrates, we have currently almost 10 reports of subjects like embedded multi-interconnect bridge, EMIB, from Intel. And advanced substrate allows a thin design and very small form factor component that could integrate it in devices with high space constraints. And today, board and substrate are sharing the same goal, provide small form factor solution with higher performances at lower cost. And to provide such a solution, two main technologies is on the market trying to fulfill this need. Depending on the integration, on the level of integration, these two technologies can be chosen. Substrate-like PCB, SLP, is more dedicated to fine line space design along with a very strict area of layer thicknesses. Whereas embedded die in board or IC substrates can overlap SLP area and address larger area of layered thicknesses and line space. And during this presentation, we will go through these two main technologies where with the application in the consumer. In the market, we could find several actors manufacturing SLP. Now, 3 smartphone OEMs managed to integrate such technologies inside their high-end product. In partnership with several companies, the 3 OEMs have shown to the world the feasibility and the reliability of the SLP manufacturing. Samsung seems to be the only one that provides different board structure depending on the chipset. And this year, we have seen that Huawei has already adopted SLPs with Unimicron as the main supplier. Every player has a different architecture and different goal. All 3 has considered stacked PCB as a solution for PCB footprint reduction and component density increase. In the iPhone XS, Apple chose to use 2 pieces of PCB and a via frame, making the connection between the 2 boards and leading to a footprint board at 1.7K millimeter square. Whereas Samsung and Huawei has only one SLP board for the RF part, stacked on top of a main PCB with a via frame, leading to a footprint at around 2K millimeter square. In this way, if we compare the actual footprint to the previous version of the smartphone using single board integration in the high-end smartphone application of each OEMs, we can see that Samsung has the higher percentage of decrease in the board area. Indeed, the OEM has the larger range of evolution due to the low density of component on the board that we have seen in the S9. The two other competitor has a smaller evolution in the range of 10% of decrease in the PCB footprint. And if we take a look closer in the Huawei case, we have seen that the company has made several changes leading to the actual integration. First, they changed the RF supplier, leading to more integration, like, for example, the use of high mid-band LTE modules from Qorvo, instead of two separated devices for Skyworks in the Mate 20. Also, they have worked with Unimicron to release a stacked board with a dedicated PCB substrate for the RF parts. And finally, when we take a look at the cross-section of the board, we can see that for the main board, a standard HDI process for the PCB is used for 12 layers and the standard line space of 13. Whereas in the RF board, a subtractive PCB process is coupled with MSAP process. And indeed, we have seen that there is only 2 layers that features a line space of around 20 microns over a PCB substrate with a total of 10 layers. In advanced substrates, the second main technologies is the embedded die. Here it's an example of the system featuring this type of packaging. Integrated Bluetooth IC along with a balloon and external component in a device with 12 millimeter square. Here it's shown that it could be done by TDK. But when we compare this solution to the separate solution, it allows a decrease of 80% of the footprint. With such form factor in automotive, the embedded is already a hard competitive application, which lead the manufacturer to look at other applications like for IoT. This example was among the first application of C-sub technologies. And today, we have seen a small penetration of this technology on the consumer world with the use of C-sub in smartphone. Indeed, Qualcomm has selected this packaging for the envelope tracking component in the iPhone X. And in this configuration, the main die is embedded in a 4-layer PCB with passives at the top in a molding compound. But we have seen that this year in the Motomode device from Motorola, Qualcomm has renewed the use of the embedded die technology for a different, but made by a different for different OEMs, and without the C-sub technologies. It's another type of embedded die, and this technology used is even more advanced with the integration of the main die in a 6-layer PCB, embedded in the 6-layer PCB. And for the API, the application processor application, a different kind of embedded die is used. In this case, the API die is embedded in a molding between 2 distribution layers. For Qualcomm, the die is placed between 2 PCB substrates, a single standard 2-layer in the top of the packaging, and a more advanced PCB at the bottom using embedded trace route technologies. And this technology has been developed by Shinko and allows a line space of almost 15 micron. Finally, copper core solder balls are used to connect both PCBs. And for Samsung, the story is different. Indeed, the last year, we have seen that using fan-out panel-level packaging, Samsung was able to embed a PMIC along with application processor die in a single package between two types of RDL. A 3-layer standard RDL at the bottom and a single-layer backside RDL at the top. And in this case, a PCB is used using embedded trace root substrate technology. Is also used, but as a via frame to connect both RDL layers. And that was for the smartphone area. But when we take a look at the edge of the consumer and the industrial world, we have seen that Intel has proposed a different way of using embedded die. For mobile computing devices, the company has proposed a CPU, a die, coupled with a GPU and the HBM stack memory on the same package substrate. The main interest for the use of embedded die in this particular application is that the connection, we can use embedded die to make the connection between the GPU and the HBM memory. Indeed, for graphical application, the bandwidth between the memory and the GPU has to be higher as possible. And this has been resolved with the use of EMIB technology. Indeed, this technology embeds a silicon die featuring direct route from the GPU to the HBM stack. And when we cross the frontier from the consumer world to the industrial, the interesting thing is that its main competitor could be the use of interposer. Here is a structure of an HPC graphical cards, and we can see that it's using a silicon interposer from TSMC as the connection between the GPU and the HBM stack. And when we compare the area of both the interposer application and the use of EMIB, we can see that if the technology from Intel could be could be licensed, it could be a hard competitor, for the interposer application. Indeed, EMIB can be mastered at the PCB level, and we need build-up PCB knowledge. But if the integration is doing right, it could be a nice point of view for the link between the GPU and the HBM. And of course, when we want to integrate more and more memory, in case of the interposer, the interposer has to be bigger, and it needs more development in terms of stitching, because the reticle from the lithography is smaller and has its limits. So thank you for your attention.
Can you hear me? All right, thank you very much, Stefan. This was a great overview of the technology. Now, Dr. Martin Strems, Director and Strategy of Business Development at AT&S, will address the status of MSAP and SAP technologies and their potential to play a key role in the heterogeneous and integration at module and system level application. Martin, the floor is yours.
Thank you, David, for the kind introduction. And thank you all for listening into this webcast. So I'd like to say a few words of, from the AT&S perspective of how we see substrate-like PCBs and also look a little bit further how they can contribute to module and to systems integration. So quickly, AT&S at a glance, then we spend a few minutes at our view of the substrate-like PCB, and some more thoughts on module and system integration examples and use cases before we will finally try to draw a few conclusions from this. AT&S overall is a PCB and substrate company, but we also consider ourselves as an interconnect solution provider in the meantime, acknowledging that PCB and substrates are important components for system build, and technology in this domain is very much merging with the packaging. With a revenue of 1 billion, we are number 3 in high-end. That means mainly the HDI SLP type technology. And last year, actually, we managed to move up a little bit further to the top space, mainly driven by the SLP. 10,000 employees and 6 plants worldwide. So among those 6 plants, 2 are in Austria, with our headquarters in Leoben. 1 is in India, and 1 is in Korea, in Ansan, and there are 2 plants in China. And the one in Chongqing is actually more towards FC-BGA type substrates that are used for processor type modules. And the one in Shanghai is very much oriented towards large volumes of high-density interconnect PCBs and also SLPs in MSAP technology. A quick overview on our product portfolio. Of course, we also do have rigid flex and multi-layer, and many of the technologies needed in the PCB domain. The focus here in this call is more on our capability to embed components and in that way take a step towards module build. Also the capability on the IC substrates, mainly flip chip BGA, and the main focus is the substrate-like PCBs in MSAP technology. So it's a mix of MSAP and HDI layers as we learned before. Some of the key applications of our technologies is the emerging, of course, beyond smartphones, of course, is the emerging Internet of Things applications, smartwatches you heard before, tablets, and a diversity of consumer, but also we see some demand already rising early on in the automotive and in industrial space. And we expect that the 5G will give SLP more momentum. As we learned, the main driver is always to have thinner boards, but there may also be some drivers on the performance side. Next one, please. So here, the next page shows a quick example of a typical SLP type roadmap. So the main feature size in lines and space is expected to move from 30-25 more towards 20 micrometer, and maybe even below. The examples you have seen before was actually, for instance, 20 micrometer lines and 60 micrometer spaces. Those you could also do in a subtractive domain. If you move to the 25, 20, and maybe even below 20, then you will really need the MSAP technology for this. Here's a brief example of a high-end smartphone with stacked SLPs. And so you can see that in this case, you can also view the stack as a first step towards a further integration, call it stacked boards, call it module, right? And this is something we generally see, that from the PCB maker perspective, there's a trend towards the modularization. And the next chart should quickly give you an overview on this. So you have the two axes to combine more and more functions in a single module, and also to make the whole module smaller. And both trends have to be accommodated, and the combination of both is also the driver for smaller feature sizes, thinner boards. And from the current outlook, the vision is something like a type of all-in-one module that combines all the key functions of an electronic device in a single stacked board, highly integrated module, you name it. A very quick recap what we actually mean by an electronic module. So very simply, it's the components plus the package, and there you also see the link to the packaging market. And of course, for a module to have a function like wireless transmission, like sensing, actuating, processing plus memory, and so on, there, of course, it's necessary also to house the active components. And so the package would then provide both the connectivity for the components and the housing. The drivers we heard before from Yole and System Plus is, of course, the time to market for such modular integration, and overall system cost reduction, the form factor, and along the way, usually also identify some performance advantage. A little side remark here. If you start to embed components, obviously you eliminate the solder bumps, and en passant, you also then have a direct copper connection to the pads that can also give you some improvement in the signals. For making modules, conceptually, there are two basic technologies. The most popular and the most pronounced one you see on the left-hand side. Here, a cutout of a Y-gig module showing the baseband system and package is usually to mount the components on the surface. Here you see a dual-side mount and then to overmold it. And obviously, with the embedding at a high level, you can create a similar structure. But of course, the process is different, that you only have a cavity locally and place the components, and then only overmold locally. So looking at the applications from the embedding perspective, we've seen before there's already DC-DC converters, and also some high-power devices, both at package and module level, but there's also applications at a larger board level where multiple power devices can be integrated for heavy electrical machines. And then also at board level, for instance, SSDs, solid-state storage devices can be an attractive application for this technology. The expectation is going forward that this will really only be used mainstream with embedding if there's a real need for very small spaces for the SSD. Before that, there's oftentimes some workarounds you can find by stacking boards, for instance, or foldable boards. So there's multiple alternative ways of doing that. There's also recently some interest in sensing to use embedding technologies. There's more to eliminate, for instance, wire bonds and to have a performance improvement. In communication modules, there's also opportunities for the embedding, not only for passives, for filters, but also for some of the active devices. And of course, as we have recently seen also from the example mentioned by Yole and System Plus before, there's also opportunities, for instance, the optical module for cameras to embed processors. And looking forward, we're sure there will be plenty more opportunities. So here quickly you see an example of a DC-DC converter. Again, the main driver for that is actually an XY footprint reduction. and with good design, you can also manage to keep the C height. The next one is the example power application, a 500-watt power application for a bridge for a brushless DC motor. On the bottom right-hand side, you can see an example of an embedded power MOSFET. Looking at the performance, you can actually see that the switching performance is significantly improved by the embedding. Conceptually, the path towards all-in-one has been investigated for a while. This is a little older demonstrator that already combines RF and computing functionality with more than 100 passives, and that could also get working devices. And we will see going forward how this technology can enter the market. The key takeaway there is, from the processing point of view, that's already becoming available. Of course, we know yield is always an issue when integrating so many components. There's, of course, some tricks and workarounds to manage that. Part of that has been also indicated in the earlier reports in the Yole presentations. So finally, a quick look at something we call FOSIP, so fan-out system in board. A side remark on how we understand the fan-out, actually taking out the bump in the signal path and having a direct copper connection. At a high level, this can usually already give good fan-out type qualities, and this is what this type of technology is intended for. It would add to a PCB substrate core with embedded devices. It would add substrate layers on top with fine lines and spaces, as you see in this example. And then you could also surface mount from the other side, not shown here, but presented at earlier conferences via copper pillars, other devices, and in this way also create some dual-sided fan-out type structures. And this, the next one shows one example how this type of concept may work going forward. Applications could be connecting passives and processors with very short signal paths. So in conclusion, we have seen that substrate-like PCBs already offer opportunity for further mainboard integration, size reduction, but they also offer opportunities for module integration applications. So in that way, there's a classical way of making MSUB type substrates, and with the maturing of the PCB type MSUB or substrate-like PCB technology, there's now the opportunity. You can also use these technologies for some of the modules, especially if the modules start to get more and more integrated and require larger footprints. With a minimum size of 30 and 25 micrometers, already demonstrated towards 20 micrometer lines and spaces and below, this SLP technology can already be a viable alternative for standard packaging substrates in quite a few applications. And with the component embedding, there is a further option for efficient module and system level integration. Thank you very much for your attention.
Thank you very much, Martin, for this very informative presentation. And also thank you all for your interesting presentation. We will now wrap up with a Q&A session. During this session, we will answer as many questions as time allows, and we will follow up via email for the remaining ones. You can still ask questions during the session. So the first question is for Mario. So Mario, question is, do functions like artificial intelligence require SLP or embedded substrates, no matter where they are used?
Do you hear me? Okay. This is a quite tricky question. Let's say artificial intelligence require SAP. Yes and no. It depends if it's on the edge or on the cloud. I would say not really if it's on the cloud. Potentially, yes, if it's on the edge, especially if it's in a mobile phone, because the first idea behind using SLP is to save some space. Embedded substrates, I would say yes. Artificial intelligence, the IC blocks that are doing the calculation for the artificial intelligence, they have a huge power consumption, and meaning that they will heat up. The heating is extremely important. So having the logic part embedded in the substrate may reduce the impact of the heat on the performance of the device. So I would say in that case, yes, for artificial intelligence.
Great, thanks, Mario. We have. Okay, so next question is for Martin. For which module application are SLPs particularly well suited?
Mm-hmm. So, from the current developments, of course, there is the wireless, RF wireless domain. And also, as we have seen, larger integrated all-in-one type modules, this is a space where SLP can make a big difference already. But overall, I think as we better and better get to know the parameters of the technology in different applications, there doesn't really seem to be too much of a barrier for other applications. For instance, there's also some ideas how to use it for cameras and so on.
Thank you. Maybe a last question for you, Martin. How do you see the trade-offs between embedding and surface mount and overall technology?
Yeah, I would, of course, the surface mount technology, I would like also to look a little bit at the questions I can see on the screen, and on the sideline answer one of them as well. So one thing, of course, is for the embedding, you'll need a copper termination surface for the embedding process, right? You can handle it within the embedding process by additional process steps, or you prefer to have die that are already copper terminated, or both is workable. So in that sense, there's no limit for the embedding to integrate die. The embedding is the newer technology. It has, of course, the advantage that you can eliminate solder bumps in the signal path, and you can reduce the signal path really to the minimum. Some of the disadvantages for the embedding versus the surface mount, of course, is less mature, and this is why it's only now, after 10 years and more of hard development, only now starting to take off. But there will be room for both types of technologies, and the surface mount, of course, can also have performance-wise a very good comeback by adding the copper pillars, and also have a very good control of the signal path. And in that way, there's room for both technologies, but ECP, from our perspective, or embedding overall, will definitely play a much bigger role in the future.
Thank you, Martin. And we have time for a last question for Stefan. So Stefan, is the SLP and stack PCB the main trend that everyone will follow in the next few years?
Thank you. It's a nice question. I think that it could be, the major application, because everyone is trying to reduce the footprint to integrate more and more functionality inside the smartphone. And as the 5G is finally arriving in the next few, and it's going to be more and more democratized in the next few years, I think that for the RF board, the SLP technology could lead for higher performances at a higher frequency. So yeah, it could be the next huge application in the smartphone world.
Thank you, Stefan. Okay, so the webcast is ending. Let me remind you a few information. You will receive within 24 hours an email that will include a link to the recorded session. Also, please feel free to share the presentation with anyone that could benefit from this information that have been presented today. Also, quick reminder, you can find all our analyses and reports on our web portal i-markernews.com. Do not hesitate to contact us if you have any additional questions. You can find appropriate contact on the last slide of the presentation. Thank you for joining us today, and have all of you a good evening. Bye-bye.